Okay, so it's 11 on my clock, so maybe we can get started. Sorry again for the mishap that happened and you got sent the readings late. I hope you were able to look at least some part of it, and I'll try to do some damage control. We'll try to go a little bit slow and see how far we get. And for the next two classes at least, I'll make sure that you get the readings at least a day, or if not more, in advance. Yeah. Okay. Great. Okay. So today we're going to talk about predator-prey dynamics. This is going to be our first sort of introduction to thinking about two species dynamics, and we're going to essentially start by talking about this Lotka-Voltera model, which some of you might have heard of. It's one of those sort of famous models. And we're going to see, it's a model where predators and prey interact, perhaps the simplest model of its kind that you could write down. And here what we're going to see is that, you tend to see cases where predator and prey populations can oscillate. One goes up, the other goes down. But there's sort of a funny sense in which these oscillations are not very good. And we will discuss what that means. In the sense in which they're not good is that these are neutrally stable orbits, and what that will mean, we will see. And so for the once we start analyzing the model, we will towards the later part of the class also talk about fixing the model, so that maybe we can get oscillations that are a little bit better, and we'll do it in sort of two steps. In the first step, we'll try and add some sort of logistic growth, which we studied in the last class, to the prey population. In this case, we'll see that actually we get hurt before we get better. In this case, we'll see that actually we lose the oscillations. The oscillations become damped. They're not neutrally stable, but they're perhaps a bit too, they're stable enough that you go to a fixed point. And then after that, we'll add this phenomenon called predator satiation, which we'll talk about, where finally we will discover that we can get these nice kinds of oscillations, which we like to call limit cycles. And in particular, we'll learn about a new kind of bifurcation, which is this half bifurcation. Yeah. So that's the sort of plan for the class. Okay. So if you saw your reading, you maybe also saw a little bit of the history of where this model comes from, right? So does anyone remember what was the origin of this kind of model? Right. So there was World War I, and something happened in World War I, right? But this is called the Lotka-Voltera model. So there are presumably two stories involved here, right? So this World War I story is which side? This is Voltera's story. There's also presumably Lotka's story, which is not in the reading, right? So Lotka's story, I guess, is a little bit more boring than Voltera's story. And so the way that these sensational things go, we talk about Voltera's story. But Lotka was thinking also about these things, and he wrote down a very similar model. In fact, they published it, very quick succession. And so, now we call it the Lotka-Voltera model. But what is Voltera's story with World War I? Was Voltera the one to discover this phenomenon that led to the development of the model? Right, yeah. So Voltera had a son-in-law by the name of d'Ancona, right? So this was sort of in the 1910s to 20s. And what was d'Ancona interested in? Yeah, he was interested in marine biology, and so he went around fish markets in the part of Italy where he was, and he was tracking the fraction of predatory species, these shark-like species, or satiations, as he sort of called it, and he observed something interesting about them that happened during World War I, right? What is it that he observed? Right. So what he saw was that if you look at time in years, and if he tracked the fraction of, let's say, predators or sharks or satiations, it was, between 1914 to 1918 roughly. Before that, the fraction was something. It suddenly sort of went up. during World War One, came back down again. This period over here is roughly World War One. And he was, this seems kind of puzzling, right? Because, this led him to maybe conclude this sort of poetic thing, which is that maybe war favors predators, right? And maybe there's some sort of poetic sense in which that might be the case. But, presumably one wants to understand this from a mechanistic point of view, right? And so where did Volterra come in this story? So one day, D'Ancona was just talking to his father-in-law, who happened to be a famous mathematician by the name of Vito Volterra. And he just mentioned this problem to him. And, that kind of inspired Volterra to write down this mathematical model. And, in a few minutes, we'll talk about how it is that Volterra explained using this model why this kind of thing might be happening. Yeah. So let's talk about the Lotka-Voltera model. So how many equations do we need to describe the Lotka-Voltera model? One for Lotka and one for Volterra, right? Yeah. So there are two equations, and I'll just write them down really quick. I hope I'm following the same convention that's in your reading. Okay, and do people agree this is basically the equations? And so where's the predator here and where's the prey? Okay, let's take a vote. So where's the prey? Is it X or is it Y? Ready? 3, 2, 1. Prey. Yeah, should I add the prey here or here? Right? X, right? That's the prey, and that's the predator. And if you forgot about this at any time, how would you quickly figure it out? By looking at the equations?
In the absence of the predator, the prey would grow.
Right, so there are some assumptions that we have about the model that can help us figure it out, right? So let's talk about the assumptions really quick. In any model that we make, we should think a little bit about what assumptions go into it. So yeah, so what are some assumptions that we're making about these dynamics? So
Absence of predator, exponential growth.
right, so the prey grows exponentially in the absence of the predator, right? And this we discussed last class, that this could be not such a great thing. Prey grows exponentially without the predator. And where do we see, which of the two terms do we see that here in? AX, right? Yeah, and so A is presumably positive, and in fact, in this, all of A, B, C, and D are positive. Any other assumptions?
When the predator is present, it brings down the population. So this actually corresponds to the rate of predator-prey reaction.
Right, so yeah, we assume that predators can eat the prey and grow as a result, right? And we model that interaction is in this sort of XY way. So what's the assumption behind modeling it in this XY way? Right, yeah, so we're kind of assuming that, this is kind of like a chemical reaction, right? There's some collision between predator and prey, presumably that needs to happen, and that happens more and more, the more and more you have predator and prey, right? So there are some mass action type, mass action like predation rate. Okay, anything else? So we talked about the prey in the absence of the predator. What about the predator in the absence of the prey? Right, the predator dies exponentially in the absence of the prey, right? And that just really means that it can really only eat the prey, right? These are like strictly carnivorous lions or something like that, right? Anything else? Is this all of the assumptions? So has anyone seen predators, on in some sort of movies, predators and prey interact with each other? Lions hunting zebras or something like that. That happens in some sort of space, right? There's often we see these movies where the lions are running after and there's this and that. Is any of that here in these equations? No, right? So what do we say is one of the assumptions because of that? There's no spatial structure, right? And so there's another word by which we often refer that to with, which is that we are modeling this as a well-mixed situation. How would we do what would a not well-mixed situation look like? What would I have to do to the, how do I see in the equations that there's no spatial structure?
If x and y are a function of the spatial positions.
Exactly, right? So x and y are not functions of space. Presumably in a version which was not well mixed, they would be functions of space. So I would have to think about x as a function of r or something like that, right? But we don't do that here, right? So in some sense, with these four assumptions, these are the simplest equations that you can write down, right? And okay, so once we write them down, we do kind of the thing that we talked about, we do in the next class when we're presenting these kinds of equations. And what is that? We ask for the fixed point, right? And what do the fixed points mean? Does x dot equal 0 give us a fixed point? Yes or no? Ready? 3, 2, 1. So I'm talking about x dot equals to 0 alone, right? Y dot can be anything. Does that result in a fixed point? Ready? 3, 2, 1. No, right? And why is that?
System is defined by both x and y. So
Yeah, exactly. Precisely. So when we talk about the fixed point of a system, we really talk about all the variables of the system not changing with time, right? So we need x dot equal to 0 and y dot equal to 0. And so there's one trivial way of making that happen, right? What's that? If there's no predator and there's no prey, so 0, 0 is a fixed point. Any other fixed points? So if I assume that x and y are not equal to 0, then I get something like that. Do people agree? And that lets us solve for x star and y star. What's that? Can people tell me really quick? D by C, A by B. Right. Okay, any other fixed points? Yeah, so that's what we were talking about, right? So sorry, you're saying x equal to 0 and y not equal to 0. Okay, what happens if x? Okay, okay, wonderful. So you're saying x equal to 0? Yeah. So that means no prey. Y not equal to 0. That means some predator. Is that allowed with our assumptions? Is there something about our assumptions that?
Like if you took one x or y, either one means 0, then other one automatically comes.
Right. Because in the so x equals 0 means no prey, and in the absence of prey, the predator dies exponentially. Sorry?
y is 0.
Yes. Yeah, so okay, so what happens if y equals 0? Right, and x keeps growing forever, right? And that we discussed in the last class is also a problem, right? So that also never reaches a fixed point, right? X goes to infinity, right? So that doesn't give us a fixed point either, right?
But if in principle, is that also a way of finding fixed point? In this case, we ruled it out that it is not.
Yeah.
But in general, if those assumptions were not there,
Right. Okay.
going by x dot equal to 0 and y dot equal to 0 simultaneously.
Yes.
It can be achieved by the cross
Yeah, there are other problems in which one way to solve both these equations simultaneously could be for you to have one of the parameters be 0, or one of the variables be 0. And we'll talk about an example of that. In fact, this case where once we add logistic growths to the prey, you'll see that now the prey don't grow forever. And so there is a fixed point where there's no predator, but there is some prey, which is sitting at its carrying capacity, right? Yeah, but I would say this is the way to find the fixed points, and of course then you have to look at all the cases, right? Okay, good. And so in the last class when we were talking about these fixed points, we always used to make this phase portrait, right? And on this phase portrait we used to draw x dot versus x. So now how many axes do we need to draw that kind of phase portrait? 4, right? I need x dot and x and y dot and y. Can one of you do that? I can't, right? So there's a slightly different way in which you make phase portraits for these for sort of 2D models. What do? Yeah, we just talk about x and y, and then we look at the dynamics in this phase space, right? And so let's mark our fixed points here. So one of these fixed points is 0. And is that a stable fixed point or an unstable fixed point? Okay, from next point onward, let's all have a vote, right? Okay, but it's unstable, and how do I see it's unstable?
Because if you have slightly more population in the system, it won't come back to zero.
Slightly more population of what?
Prayer to report.
Okay, so good. So let's try and ask what happens if we sit at x equals 0, y equals 0, and we add a little bit of the predator. Okay, if I add a little bit of the predator, where do I sit? Do I go up or do I go right? Up, right? And what happens if I go up? Do I draw an arrow that's going up? Or do I draw an arrow that's going down? Ready? 3, 2, 1. Down, right? Okay, so at least it seems to be stable in this direction. What about if I have nothing but I add a little bit of prey? Do I go right or do I go left? Right. Right. So then is this a stable fixed point or an unstable fixed point? Ready? 3, 2, 1. Unstable, right? Okay, so the 0, 0 fixed point is unstable, right? And so in principle, even if we find one direction where you go far away, it's an unstable fixed point, right? Let's talk about this other fixed point. This is really the really interesting one, right? And I think it's sort of worth talking about what this fixed point means and what it's saying before we talk about its stability. Because in principle, the fact that this fixed point exists means that the model makes some rather striking predictions. So let's try and do a problem that we'll all work out on our own first, and then we'll talk about it. So let's say that we have a system with a predator and a prey, let's say in some forest reserve. Let's say I start hunting the predator, right? I literally go in and I start shooting bears or something like that. Apparently this is allowed in some countries. Okay, the question is, and yeah, let's say that we're sitting at these sort of fixed points. What happens to the predator population? Okay, and I'll give you a few options. Does it 1 increase, 2 stay the same, or 3 decrease? Okay, take 5 seconds to think about it. Is the sorry? Yeah, so there's a reserve, there's a predator, and there's a prey. Yeah. Now I start going in and start artificially hunting the predator. And the question is, what happens to the predator population? Does it go up? Does it go down? Does it stay the same? Okay, and we're assuming that the predator and prey follow these dynamics, yeah? Okay, shall we have a vote? Ready? 3, 2, 1. Still don't see everyone voting. Oh, sorry. Yeah, you can say 1, 2, or 3 based on what you think your response is. Okay. Okay, I would say most of you are saying no, it won't change. And can someone say why?
Increase the D.
Right. When I'm going in and hunting things, I'm increasing D presumably, right? So this means D goes up. And my predator population presumably is Y star, right? And so does Y star change? No, right? But this is, right, so mathematically we can see that it won't change. But this is kind of a really surprising prediction of the model, right? Right? Let's just quickly talk about what happens to the prey population, because that makes it even more surprising, I'd say. So what happens to the prey population? You have the same options. We'll all think about it alone and then we'll vote. Okay, does the prey population increase, decrease, or stay the same? Ready? 3, 2, 1. Yeah.
For the same condition.
Yeah. Sorry. For the same situation. Yeah. People don't seem to be committed to. Yeah, I would say half the class does not want to commit to an answer because I'll go and catch them or something. Okay, I'd say most of you are saying that goes up. And why is that? Right, D goes up, and so X star goes up. But that's also surprising, right? So what this is saying is that if I go in and start artificially hunting the predator, nothing happens to the predator population. The prey population will increase. So why is this happening?
Predation, so prey population.
Less predation, but my predator population didn't change.
See, when you're hunting, the population of the predator goes down, but due to that, the population of the prey will go up. So,
but the population of the prey of the predator did not go down, right?
Net effect, like when you're hunting down predators,
Yeah.
you're removing some predators. So the remaining predators will have more prey. So they'll have more chance of encountering a prey. So that will again restore the predators population.
Okay, but then once it's restored, what happens to the prey population?
The predator.
This is just the fixed point which we are looking at.
Yes,
not-
yes.
So XY would mean the number of prey and number of predators at some time.
That's right.
But what we're seeing, this observation is solely for only at the fixed point.
That's right.
How the fixed point moves with change in D and not how the system behaves.
You are correct, though it'll turn out, and we'll talk about it in a few minutes, that, so we won't prove it, but actually for this system, you can show that even when you're not at the fixed point and the populations are changing, the time average population sizes actually are the values given by the fixed points. So there is a sense in which, this is some well-defined number, right? Anyone else have a reason, maybe a reason that's in the equations at least?
Qualitatively, if we say that the fixed point moves, then the trajectory is around the fixed point, however they are have to move. So
Yeah.
it makes sense to say that the time averaged.
That's correct, but we aren't even talking about the trajectories, right? We're only talking about the fixed point. So the fixed point, just to see on this phase plot, where did it move? It moved right. No? You increase hunting on the predator and you move this fixed point, right? Right? So the reason really is kind of here, right? The fixed point means that two forces are balancing each other, right? There's a force of death, and there's a force of hunting, right? And this force increased. So at a fixed point, this force has to balance it. And so, if Y star is not going to change, X star better change, right? Okay, good. So, just to sort of point out that there are some pretty surprising, sort of qualitatively interesting predictions that the model makes, and whether or not you can go up and read whether or not these things are used as policy predictions for park rangers in various countries, right? So this is our fixed point. Let's talk about the stability of this fixed point. What do we do to check the stability of this fixed point? Can I do the same thing I did here, that I just add a little bit of one or the other? You can, right? And what will you find? It moves in one direction. Which direction? So if you add a little bit of prey, if I'm here, which direction do I move in? Sorry?
I thought you were talking about this.
Sorry, yeah. So you're right that to inspect the stability of the zero fixed point, I have a cheat, right? What about to inspect the stability of this fixed point? So did people do the reading and read about linear stability? Okay, so what do we do? Sorry? You compute the Jacobian at that point, and what's the Jacobian? Sorry? Right, it consists of the matrix of the partial derivatives of what quantity? What's F?
So we define an F over here, some of the function, arbitrary function for the 2x or the y. So we take them as functions and then compute the Jacobian for those.
Yeah, so you're right that yes. So you have, we have some equations of the type f x dot equals f of xy, y dot equals g of xy. Sure, and why should I want to compute the partial derivatives of f and g with respect to x and y? Right, so this is what we are proposing, right, to compute this quantity. Did I have that right? Why should I do this?
The linear approximation of the system about the point at which it lies.
I think maybe with the Taylor series, two variables.
Sure, but why?
We'll have a linear perturbation, small perturbation like, and in this sense we'll add x star plus theta.
Yeah.
We'll expand to the Taylor expanding and complete the first term of theta.
Okay, great. Yeah, so what we do, and this is an important sort of concept in all nonlinear dynamics, is that you're sitting at a fixed point, and of course when you're sitting at a fixed point, f and g are 0, right? And then what you want to do is you want to go a little bit farther away from the fixed point, right? So let's say you go to a point which is, x star plus epsilon 1 and y star plus epsilon 2, right? You perturb x and y by some amount, and then yeah, you do Taylor series, etc., etc. So why are we doing that? Right, our phase portrait is an x and y, but what we really want to know is, if I perturb my x and y by a small amount, here epsilon 1 and epsilon 2, can I derive an equation for the dynamics of these perturbations? Why do I want to do that? Because I want to know whether over time that perturbation will grow or die or do something else, right? And so you can effectively find out from these equations that when epsilon 1 and epsilon 2 are small, basically you get equations of this form, right? Which are basically something like this. We have epsilon dot equals this matrix J times epsilon. Right, and that's where you have to use your Taylor series, etc., etc. And is this Jacobian just, these partial derivatives of functions? Is this a matrix that's computed at a specific point? Right, it's computed at the fixed point at which you care about, right? And why do we care so much about it? Right, so the perturbation is around the fixed point and we want to know whether this perturbation grows or not, right? And so for that we need to solve this equation. Anything special about this equation that helps us solve it? Right, why should we care about the how is this an eigenvalue equation? Right, yeah, I mean this is a linear differential equation, right? And we know the solutions to that depend on the eigenvalues of this quantity. And in particular, if we want stability, what do we want about the eigenvalues of the Jacobian? Sorry?
Magnitude should be smaller than 1.
Why should the magnitude be smaller than 1? What's so special about 1?
1 is say, okay, so if it's smaller than 1, it will decay. If it's 1, it will stay the way it is, and if it's greater than 1, it will grow up.
Why?
Because the solution would be e to the power.
Yeah, so your epsilon will be something that's e to the power what?
Eigenvalue.
Something like that, right? Okay, so now can you make sure you're arguing about your 1 or not 1 again? Yeah, so what happens when the lambdas are all 1? This becomes e to the t, right? What does e to the t do at long time? It'll diverge, right?
Yeah.
So should we care about it being larger than 1 or some other number? 0, right? So, and does this lambda have to be a real number? It can be a complex number, right? So anything specific about something being less than 0 or greater than 0? Someone else? Yeah?
Yeah, if it's smaller than 0, it will decay.
What is smaller than 0? But what if it's a complex number, then? Right, so you care about the real part of all of the lambdas, right? And you want all of them to be less than 0. And if that's the case, then all of these solutions will decay to 0 at long time. And that means whatever perturbation you did will eventually die and you'll come back to the fixed point. And that's the definition of being stable. What would instability be? Yes, correct. Instability would be not stable. But what would it mean in terms of the eigenvalues? If any one of the eigenvalues was positive, then we are screwed, right? If any eigenvalues have a real part that's greater than 0, right? Okay, so can someone tell me very quickly what the Jacobian for this model is at this fixed point that we care about? This is a residue point. Should be fairly easy to compute, right? Okay, let's write the general one and then we'll compute it at our fixed point. So our fixed point was what? It was D over C and A over B. And just check if I'm doing this right. Do people agree? And if I put that in, will I get this? Yeah? No? I did something wrong? Okay, great. So, okay, we computed the Jacobian at our fixed point. How do we get the eigenvalues? Right, I should care about the trace and determinant. And what does the trace and determinant tell me? That's a sum. And what's that? And what's the determinant? It's something, but is it negative or positive? I guess that's all I care about. Negative, right? Sorry, yes, positive. Okay, good. What does that tell me about my eigenvalues? Can both my eigenvalues be real? Why is that? So this means that they're equal and opposite. Sorry, yeah, that one is negative of the other. So they're both real. Can you have two real numbers that are like that? That have a product that's positive? No, right? So what does that mean? They're purely imaginary, right? And in particular, you can calculate it. In this case, your lambdas will be plus or minus, I believe, AD times iota. Root of AD times iota. So do we have stability or instability? There's one case we didn't take, right? So what happens when the real part of these lambdas is 0? Right? Both of them have real part which is 0, right? So does this perturbation grow or die? Neither, right? Neither grows nor dies. So there's a third case, which is what this is, which is that it's neutrally stable. This means all the real parts are 0. Right, and that's the case that we have. And okay, so they neither grow nor die. Do they just stay there? This is e to the I root AD iota, e to the I root ADT, right? What does that look like? That's that's a sine or a cosine, right? So these things will go around in closed orbits. Right, and in particular, you can get solutions for both the predator and the prey, right? And will they both have the same? Yeah, will they be in phase? Sorry, pi by 2 phase difference, and how do I see that? The minima of x.
And the minima of y are like pi by 2.
Yeah, basically, yeah. So you can just look at the orbit and say, look, their minima are shifted from each other by a phase difference of pi by 2, and that does it. You can also go and compute using this solution, and you can see that one is basically like sine and one is like cosine. And so those also have a phase difference of pi by 2. Okay, so this gives us these closed orbits that we care about. Do they have to be circles? They can be some shape, right? Okay, but I'm also making these closed orbits as I go farther and farther away. Am I justified in doing that by what we just did? Right, so I know that when epsilon 1 and epsilon 2 were small, we just did this elaborate argument for why these things should be closed, right? But it's also true that if you try and simulate these equations, where epsilon 1 and epsilon 2 are not small, so certainly here they're not small, then the equations still give you closed orbits, right? But they didn't have to. Why is that?
In doing this analysis, we're assuming that the nonlinear terms are negligible,
Yeah.
and here we're getting a 0, but even if the nonlinear term is small enough, it can shift it to like be either less than or greater than 0, and you could have some sort of behavior that's not accounted for by this.
Right. I mean, I think what you mean is that when epsilon 1 and epsilon 2 are large, then the nonlinearity is not small anymore. You can't ignore it, and that can do things that can cause differences, right? So would there be any case in which, yeah, are there any kinds of equations or any kinds of forms of f and g where you wouldn't have to worry about the smallness of epsilon 1 and epsilon 2? Linear functions, right? So if f and g were linear, and you still found that your eigenvalues were purely imaginary, then it would be the case that epsilon 1 and epsilon 2 need not be small, right? Because there we don't have a nonlinearity at all. So there's nothing like this nonlinearity becoming big and messing things up that we have to worry about, right? So there are these three cases. If we have linear equations, then linear stability sort of close to the fixed point tells us also the behavior far away from the fixed point, right? Then there's the non-linear equation where you go a little bit far away from the fixed point and you get purely imaginary eigenvalues, but that doesn't have to give you closed orbits over here. And yet this system, this is where it gets confusing, does have closed orbits even when you go far away from the fixed point, right? But I just want to make clear that this didn't have to be the case. And certainly linear stability is not the mathematical reason why this happens. In fact, there is a whole reason which has to do with the fact that this system of equations has a conserved quantity, and because of that constant of motion, you can go ahead and show that the orbits will be closed. But if you're interested, I'll leave you to sort of look that up online. And if you're interested to talk to me about it, I'm happy to do it, but I won't work it out and talk about it in class, yeah? But just be careful that in this system, what we just did was showing that there are closed orbits only close to the fixed point. And yet it's true that there are closed orbits even farther away from the fixed point. Okay, final thing about this, how do we figure out the direction of these orbits, whether they go clockwise or counterclockwise? Okay, I can tell you my trick, which is that even if you forget about this, you know that your unstable fixed point does this. So you know in the limit when you go farther and farther and get closer and closer to this, the arrows shouldn't suddenly change. So if you ever forget about it, just remember what the trivial fixed point does. Right? The other way to argue for it is, of course, you know how causality goes. Once predator populations only grow once prey populations are eaten, right? So the other way around, you can see actually would violate causality. Okay, so let's quickly talk about this question that we started with: war favors predators. So So does this whole thing explain D'Ancona's observation? Did Volterra just take him around for a spin, or did he actually provide an explanation for why war might be favoring predators? So what could be one thing that's in the model that's changing during war? Death rate of the predator. Why is that? Maybe people go out to fight a war, and so there's less fishing, right? And it's not necessarily, people are fishing both kinds of fish, right? They're fishing for predatory fish and prey-like fish. So presumably the hunting rate of the predator is decreasing, and the hunting rate of the prey-like fish is also decreasing, right? So what does that do? So okay. So I guess what happens is that during war, D increases. Has anything else happened? What about A? Sorry. D decreases. A increases. Why is that?
inherent growth of the prey and the death rate of the prey. So you're reducing that death rate, which would increase A.
Exactly. So that A, as we studied in the last class, is a combination of birth minus death, right? So decreasing the death rate is effectively increasing this A, right? So the net birth rate, the net birth rate increases. And so what does that do to our fixed point over there? You know, to remind you, our fixed point is D over C, A over B. So what happens to this? It goes down. This one goes up. And so what happens to the ratio of predator to prey? It increases, right? And so that might explain, that might be one non-romantic explanation of why you suddenly see in these markets, you know, there's a dual effect. Not only are the prey decreasing, but the predators are increasing. That's why maybe it might be very easy to see the fraction of the predatory fish suddenly go up during wartime, and also explain why once you take that away, once war ends and these DNA go back to their original values, why you might go back to the original fraction.
We talked about apex, like are it at the top of the food chain? Because
That's a good question. I think that he was just doing kind of like a survey at that point. He wasn't that interested in looking at the entire food web. I think he was just going to the fish markets and really doing a survey of what kind of fish he saw. And I think this is the way that he classified it. But I don't read Italian, so I mean, I've looked at this paper, but I haven't really looked at it in that much detail to see whether he really did this food web kind of analysis. Okay, good.
This model,
Yeah.
why should it be, like, I understand this explained.
Yeah.
But why should it be correct? Because we missed a lot of things.
Yeah, it doesn't have to be right. In most of science, we're trying to find explanations for phenomena that we see that make sense. And whether or not it's actually the reason, you know, will take much harder work to figure out. So in the spirit of having a simple model that could explain this counterintuitive observation, in that spirit is what we're talking about. Yeah. Okay. All right. So, you know, there's one of the assumptions of this model that we were talking about, which was this assumption that the prey grow exponentially in the absence of the predator. And we might want to change that. Why is that? There's some reason that we don't like these neutrally stable orbits.
You do a perturbation, it just makes me one out.
Yeah, great. Yeah, if you're on some orbit and there's some noise, you know, so something becomes larger or smaller, you can just go and sit on another orbit, right? And so what that means is that these oscillations don't have any characteristic time period or amplitude, right? The amplitude you can see very easily. If you go over here, your amplitude will increase. You know, you go over here, closer to the fixed point, your amplitude will decrease. In fact, your time period will also change. Right? And again, this time period that you calculate from this analysis is not necessarily going to be the time period for the things that are far away, but you can see that also changes. So in some sense, these oscillations, you know, you see the oscillations, they have this fixed phase difference, but they don't have a characteristic amplitude or time period. And so in that sense, these are not the kind of oscillations that we like to see. Why is that? Have people seen data of predator-prey oscillations? And typically they do seem to have a characteristic time period and amplitude. Okay, so let's see how we can get that. So the rest of the class we'll try to work towards getting that, right? So what we're going to do is the following. We're going to add this logistic growth to the prey. And we can see why, right? We already discussed that the prey grows exponentially in the absence of the predator. And for some reason we don't like it, because that doesn't make sense. So which of my 4 terms in my predator-prey equations should I change to add logistic growth to the prey? The A term, right? So I can make it something like this. Okay, how many fixed points will this have? Okay, think about it for 5 seconds, and then we'll all answer using our fingers. Okay. There won't be more than 10 fixed points, so your fingers will suffice. You folks already worked this out earlier in class today, so you will probably know. Okay, let's have a vote. Ready? How many fixed points? 3, 2, 1. Everyone's confused. Okay, how many fixed points did the original Lotka-Voltera model have? Ready? 3, 2, 1. Okay, so your fingers all work. Good. So how many fixed points does this one have? Well, you can at least check if the old ones still work. Ready? 3, 2, 1. I won't eat you if you give the wrong answer. Okay, I would say that there's a mixture of 2s and 3s. So why don't you turn to your partner and discuss what you think the answer should be and why. And please, I encourage you to talk to someone around you, even if they agree with you.
So I just remove the x. X 0 0 is 1. Now I remove the x, I remove the y over here. So this will be shared condition. So d by c x equal to d by c, y equal to yes. Now you are fixing the x to get d by c order. So you don't have any control over it. So you will get y single one.
Okay. All right. I saw some conversation happen, so that's good, and it seems to have died down, which is also good. All right. Let's take a vote again. How many fixed points does this model have? Ready? 3, 2, 1. Okay, I would say most people who are responding with 3. Great. Okay, and can someone say which 3? Okay, 0, 0. 0, 0 is still a fixed point? Yeah, good. And is it still unstable the same way that we had before? Okay, great. 0, 0 is 1. Perfect. K, 0, right? So that's a new fixed point. Right? And there's at least one direction in which we come into it. What about this direction on the right? This is just logistic growth, right? This is just in the absence of the predator. But okay, is it stable or not stable when you add a little bit of the predator? Okay, so let's see. Let's say we're sitting at this fixed point where x equals k, x equals k, and we add a little bit of the predator, right? And what do we want to ask? We want to ask if the predator grows or not, right? Because if the predator grows, you go up and you're unstable, right? And if you go down, then of course you're stable, right? So we only need to look at y dot when y is small and x is k. Right? And what is that? Let's say we add some amount epsilon. And so when is this positive? Can someone see something? Can this be negative ever? Yeah, when D is greater than Ck. Can this be positive ever? Yeah, when Ck is greater than D. Right, so depending on what we have, it's either going to be stable or unstable. Right? Okay, so let's just consider a case where this carrying capacity of the prey is large. In that case, let's vote. Is this fixed point stable or unstable? K is large. Is this point stable or unstable? Ready? 3, 2, 1. Unstable, right? You'll go away and this becomes unstable. Okay, so those are two. What's the third fixed point? Right, it's something sitting here, right? And I think it looks like D by C, A by B, 1 minus C by dk, something like that. Okay, so question. Okay, so first of all, we better check that this works in some limits, right? Every time we work with something, yeah. I think you're right. Maybe I did the algebra wrong myself, but okay, this won't matter for what we're doing for a second. Okay, so what was the previous case that we had before? Is there a limit in which this model becomes exactly the model that we were working with for the first half of this class? K tends to infinity, right? And when K tends to infinity, this fixed point better become our old fixed point. Does it? It does, right? So when K goes to infinity, this term goes to 0, you go back to your old fixed point. Okay, good. And as K becomes smaller and smaller, which population's fixed point abundance changes? Is it the predator, you vote up, or the prey, you vote down? Ready? 3, 2, 1. So I'm changing K now. I went from K to infinity to some finite number, and I'm decreasing it, and I'm decreasing it, and I'm asking what's happening to the fixed point abundance of the predator and the prey. Is the prey's, is it prey changing? Let's just give prey changes. Yeah, let's just vote like this. The data changes, votes change, or neither. Okay, ready? 3, 2, 1. Okay, yeah, most of the people think it's the predator's population changes. And again, that's, we can see, right, we made a change to the prey's population dynamics, but it's a predator where we see the things. This is the same sort of behavior that we used to see before. But now you can work out the stability of this guy, where you'll really have to work out the Jacobian again. And I'm not going to do it in class. But at this point, you're going to see a Jacobian, which is going to have a trace, which is going to look something like maybe AC by dk or something like that, or AD by CK, but that's going to be negative. And you're going to see a determinant that's going to be positive.
That one is only for that fixed point.
That one is only for this fixed point. Correct. So when I'm talking about the Jacobian, I'm talking about the Jacobian of this fixed point. These two fixed points we determined are unstable, right? Yeah, so we're really now interested in the stability of this guy. And if this one also turns out to be stable, unstable, then we really have to think about what's going on in this system, right? So we better hope that it's stable. So okay, so can someone tell me based on this argument what the stability of this fixed point should be? Why stable?
Both
How do we know that both eigenvalues have a negative real part?
Some of the eigenvalues is negative.
Some of the eigenvalues is negative.
The product is positive.
Minus into minus equal to plus.
Right, so both of the eigenvalues would have a negative real part, and that means stability, right? And so you can work this out and show, and so in this case the trajectories, instead of looking like closed things, will look like stable spirals.
So this imaginary part corresponds to the spiral.
Yeah, the imaginary part is what gives you the spiral behavior, and the negative real part is what gives you the sort of falling in behavior, right? So in this case, if we were to look at the dynamics, let's say we were to plot, what the actual predator and prey population, what time would look like, what would they look like? What do they look like? Will they decay to zero?
Oscillate and decay.
Right, they'll show damped oscillations, right? And the other one will be, again, you'll start off with a pi by 2 phase difference. And then, I probably didn't draw this right. Yeah, but the point is that you'll see damped oscillations. Right, so if you wait a long time, you wouldn't see any oscillations at all. That's a problem, right? So why did this happen? I made such a small change to the model. I just added this little bit of logistic growth to the prey, and I went from having these beautiful closed neutrally stable orbits to a stable spiral which shows me damped oscillations. Why did this happen? Does someone have a guess of what's going on? So people often say, and this is often people who are much more mathematically inclined, that the Lotka-Voltera model is a bad model. And it's not bad in the I don't like it because I don't like Lotka or Volterra sense, or because it's not realistic. But it's bad in a very particular mathematical sense, in that it's structurally unstable. So I want to talk about that for a couple of minutes. So does someone know what the structural instability means? This is not dynamical instability, by the way. What we were talking about thus far, you perturb the state of the system away from the fixed point and you ask where it goes. That's what's called dynamical stability. We're talking about something else. We're talking about structural stability. And that's, okay, I'm going to become a little bit, very conceptual for a second, but say that we're talking about a phase space of models. Yeah? So let's say we're talking about a space of, all possible models that you could make, of this kind. Right? And let's say we care about those models which give you this kind of fixed point that we care about. Right? And say that we're interested in the dynamical stability of this. Right? We already talked about the fact that it's a trace and the determinant of this Jacobian that we really care about. Right? So maybe what I should draw is, I should draw in this phase space the trace and the determinant of this Jacobian. Right? And I know where I am here, where I'll get stability. Right? That's when the trace is negative and the determinant is positive. This is the stable region. Right? And if you want to read more about, seeing where exactly this comes from, you can either work it out the same way that we worked it out before, or you can also read Strogatz. Strogatz is a very nice discussion of this in this chapter on linear systems. And over here, you can work out with the same logic that we worked out right now, that in this region you're unstable. if your determinant is positive, that means one of the eigenvalues is positive, one is negative, the product is still negative, the sum is still negative. So you become unstable, and over here you get something else, right? So where is the Lotka-Voltera predator-prey model sitting in this space of models? Trace equal to 0 and determinant was positive, right? So somewhere here, right? Now let me describe to you what I mean by structural stability. Say that now I perturb the model, right? One of the ways in which I perturbed it is here, right? I added this extra assumption to it, right? What would generically happen to the stability of this model? On this line, I'm neutrally stable, right? What would happen generically to the stability of this model if I perturbed the model, if I made a slightly different model? You'd either go up or you'd either go down, which means that new model would either be stable, when we saw an example of that, or you could do something else to it, and it'll become unstable, right? And so that's a sense in which it's bad. But why is that? Why is that bad? Is there a property that we should ask from our models that, if you make a slight change to the model, the qualitative behavior of the model should not change? Right? And would this Lotka-Voltera model do that? No, right? It's sort of sitting on this edge case where a slight change to the model itself can make it have very different behavior. We saw an example of this. And so it's in sort of this sense in which people tend to talk about the Lotka-Voltera model being bad, in that it's not very stable to perturbations in the model itself, right? And so this is an example of that. Okay, so this doesn't give us the damned oscillations. Sorry, this doesn't give us the oscillations that we want. It gives us damned oscillations. So what do we do to get some nice oscillations with a defined amplitude and time period? Let's talk about our phase space. So our phase space can't look like this, right? Our phase portrait. We discussed that it can't look like this either, right? What was wrong with it looking like this? No characteristic time period or amplitude, right? So what would a phase portrait look like which would have oscillations with a characteristic time period and amplitude that did not decay away with time? Right, it would have something called a limit cycle, which would mean that there would be one orbit, doesn't have to be a circle, but one orbit. What's the difference between this and that? Yeah, if you go away from this orbit, the dynamics would bring you back to this orbit, right? So in some sense, this cycle, this orbit itself would become an attractor. And in that sense, you get what's called a stable limit cycle. You can also get an unstable limit cycle where you have an orbit, but if you perturb away from it, you either go inward or outward forever.
These models are present right?
So currently, we haven't seen a model like this. This is the kind of model that we would like to make. Right? This is the ideal to which we are aspiring, and we're going to do that now. Ideal model behavior. Right? So this was the Lotka-Voltera predator-prey model. Has oscillations, but they're neutral. So we don't like that. You add predator carrying capacity, some prey logistic growth, some prey carrying capacity. You find that you always get stable spirals. So now we want to change this further and hope that we get something like this. Okay, so what's you kind of know what we did in the reading. So what do we do? So you add something called predator satiation. What does that mean, satiation? Has anyone encountered this word before? We're going to have lunch after this. We often talk about satiety. What does that word mean? Yes? Right, yeah, it's some notion of being satisfied with, I've eaten enough, I'm satisfied, I don't want to eat more, right? So what would it mean what could it mean in the context of the predators? Yeah, let's say there are tons of prey. Tons and tons and tons of prey. And few predators. Would you still expect the predation rate to keep increasing further and further and further and further? No, right? You expect it to kind of saturate. The predators are going to eat something, and then they're going to be like, okay, I'm going to stop now, or I'm not going to eat as fast as the prey are growing. So you want this term, and consequently this term, to saturate in the limit of large X, right? You want saturating predation rate when X is large. So how do we do that? So you want to make this bxy term into a saturating term with X, right? Someone know the simplest mathematical way to make that happen? 1 minus r over x. I see. So you're saying that basically you want to make this also logistic type. There could be some problem with that, right? There you're saying that that's almost as if the prey are growing, and because of the now the predation rate depends on the growth rate of the prey, right? That's kind of funny, right? So one way of doing it, apologies for the kappa, but we'll call it kappa m maybe, is to add this kind of term. It's called a monoterm, and you might have encountered something like this also if you've studied Michaelis-Menten kinetics. What does this do? Why does this work? Let's draw the predation rate now as a function of X. So what was it before? Let's say Y is fixed. So Y is fixed, what does this look like? The predation rate looks like a line, right? It's B, X, Y. That's what it looked like in the old model, right? The larger and larger X becomes, the larger and larger the predation rate becomes. So what would this term do now? Yeah, it will saturate. When will it saturate? So let's say X is very, very large. Large compared to what? Yeah, to kappa m. What does this term become in that limit? B times Y, right? This becomes X over X is 1. So some limit in which the maximum value that this can take is B times Y, right? And so when X is very large, you get a function that looks like this. What happens when X is very, very small compared to kappa m? Well, when X is 0, it's 0, correct? What about when X is not 0 but small compared to kappa m? So now X is much smaller than kappa m, so you can ignore this. So this looks like a line, right? What's the slope of the line? Is it B? Yeah, B over kappa m. So that might be a higher or lower number depending on the value of kappa m, but it's a line again. Right, and some point the line meets this saturating behavior, and you see this. So what's kappa m then? What's so special about the value of kappa m? Right, so at some point this predation rate becomes half of the maximum value it's going to take. Right? What's that value of x? Right, at x equals kappa m, this becomes 2 kappa m, that's kappa m, you get by 2, right? So kappa m is sort of the prey population size at which the predation rate is half its maximum value, right? So in many cases for these kinds of terms, these are called half saturation constants. Okay, so now this term does this saturating behavior that we want, right? Okay, maybe I'll ask the same question again. Can people anticipate what the question is? How many fixed points does this model have? Think about it for 10 seconds, but please think about it, and I want people to answer. This class doesn't work if you don't participate. All right, so how many fixed points does this model have? Let's all vote. Ready? 3, 2, 1. Okay, some people in the back just don't want to answer. Okay.
Does it depend on its value? The X is very large.
Yeah, okay, good. Nice question. So remember, we're talking about this space of x and y, right? So in this case, x and y can take any value as long as it's, neither of them are negative, right? So the fixed point, you're right, could lie anywhere, even when x is very, very large, right? So I wanted to think about where all the fixed points might be. Okay, sorry, let's vote again. Ready? 3, 2, 1. Okay, for the people who are answering, they're all saying 3. For the people who are not answering, I don't know what you're afraid of. But okay, so most people are saying 3. Can someone say which 3? Maybe someone in the back? Sorry, I really don't mean to pick on you. Can we name some of the fixed points? 0, 0, okay. Anything else? K, 0 is still a fixed point, right? And any others? There's another one somewhere in the middle, right? Somewhere sort of sitting here. Okay, and so now we want to talk about the stability of these points, right? So what about the stability of 0, 0? Is it stable or unstable? Ready? 3, 2, 1. Unstable, right? And it's unstable in the same way as we've had so far. You know, we haven't changed that part of the model at all. What about this x equals k, y equals 0? It again depends, right? It again depends how it depended before. But there might be cases where it's stable, there might be cases where it's unstable. Okay, so let's say we consider the case where k is large enough so that it's stable, so that it's unstable. Okay, now we really care about this fixed point, right? So again, I'm not going to work it out, but you can do it. And what you'll find is in this condition, this fixed point also turns out to be unstable. So what do? Last time we got away with it because we found that this one was at least stable, so we had these stable spirals. Now all of our fixed points are unstable. What will the dynamics do? So system is going to do something, right? Okay, so one of the things that it could do that might make it very bad could be that everything goes and blows up to infinity, right? So first we want to check whether or not that's happening. So let's do the following thing. Let's just draw a box somewhere in our system, right? And let's just see what the dynamics are sort of doing, at the edges of this box. What would happen if these dynamics were such that things were diverging to infinity? There'd be a flux going out, right? At least somewhere. And if that were the case, then we wrote a bad model and we need to go back to the chalkboard and do something else, right? And if that's not happening, then maybe everywhere in this box you come back inside, then you know that, well, you have to stay within this box, so something might happen, right? And maybe that something is this ideal behavior that we were looking for, right? Okay, so do people get this box argument? And if you get this box argument, these are exactly what the Kolmogorov conditions are about, right? They're about taking this kind of box and computing these fluxes, right? And the fluxes have to do with df, or dou f, dou x, dou g, dou x, and so on and so forth. So what's dou f, dou x? That's how the prey population is changing as you increase a little bit of x, and you want to compute that at large x, right? And now we're not computing it necessarily at some fixed point, right? And so when you compute that, that's exactly what we did in the reading. You'll see that all of these arrows come back in, right? So they either kind of stay along the boundaries or they come back in, right? So that means that we're not diverging. Okay, that's good. But this in itself, okay, this at least says that we are allowed to have some sort of cyclic behavior, right? Well, okay, you don't diverge to infinity. You're not going and sitting in any of the fixed points. You must do something else. But it need not be periodic, right? It could be aperiodic. It could be some sort of chaotic behavior. So how do we show that in this case that's not true? We use some sort of theorem.
Tends to infinity, we would show that it converges to a limit.
That's what we have to do. At t going to infinity, we have to show it that it converges to a limit cycle. But how do we do that is the question. So we use something called the Poincaré-Bendixson theorem. Oh dear. Was there an S? Okay. What does the Poincaré-Bendixson theorem say? So what it says is the following. Say you find some sort of donut-shaped region in your phase space. That's this donut-shaped region, say, where two conditions are satisfied. All of your trajectories flow in, or at least don't go out on one side, and all the trajectories go out on the other side. If that's the case, then you will have a limit cycle somewhere inside that donut-shaped region.
I'll be really more conditions not needed, like concentrate or something.
Oh, yeah. Yeah, but that we know in this case that we have. Right? Yeah, so this was a very mathematically irrigorous statement of the Poincaré-Bendixson theorem, right? Okay, so we satisfied this bit. What about this bit?
Unstable.
Right, it's an unstable fixed point, right? So these, there's going to be some point, something in the boundary here where we're going to be able to draw these things going out. And in this case, now, yeah.
But if it's something like the 0, 0 where one thing is coming.
You're talking about the 0, 0?
Yeah, so
Yeah.
thing in the y-axis is coming in.
Yeah.
So there's no circle.
Correct. So yeah, so you know that your limit cycle cannot contain this point.
But how do we know that our this other fixed point doesn't behave in the same? Like there might be one direction in which there is it is stable, right?
So, but we computed all the fixed points, right? And we showed that all of them are unstable. So we know that we will not be sitting at the fixed points at long time.
It's unstable if there exists one direction along which it
Yes.
it diverges,
Yeah.
it comes out, right? But there might be one direction in which it tries to come in.
Yeah. So
So you can't find like a circle where all the at all points it is going out. It might be.
I didn't follow. What do you mean by you can't find a circle where at all points it's going out?
You told that you can find a loop around the fixed point, where
Around this fixed point, right? Yeah.
that at all points on the loop the thing is going outwards.
Yes. And that's this one, right?
Yeah, but it might. How do you know at all points on that thing it is?
Oh, well, I can show you that you can find at least one, right? You go epsilon away from the fixed point, and you know that no matter which direction you go in, you will get a perturbation which grows, right? So that means if you take a circle of radius epsilon, that one at least satisfies this property where everything is going out.
But wasn't the
Yeah.
definition of unstable being that
Yeah.
only like if there is just one direction where the perturbation like goes away,
Yes,
it's unstable, right?
correct. But in this case,
All directions.
all directions are unstable. So in this case, one of the directions was not unstable because one of the eigenvalues was negative, one of the eigenvalues was positive. You can go and compute that. In this case, both of the eigenvalues will have positive real part. So no matter which direction you go in, you'll go up.
Can we draw the donut for x equal to 0, a and 0, 0 as well? Can we apply this?
The problem is that this outer boundary is really not well defined when you go on this side of the donut, right? So you can't have a limit cycle surrounding this, right? But there's one last thing I want to point out here, which is that this didn't always have to be the case in this model. This was only the case where we chose our k so that this fixed point was unstable, right? So the other thing that can happen in the same model is that you can have this point be unstable, this point be stable, and then in this case, this point will be unstable, and all the trajectories will kind of flow into here, right? And so depending on how you choose your parameters, you'll either get limit cycle oscillations of this kind, or you'll get things that die where the predator always dies. Okay, and that will happen as you change one of these parameters, and so now you can draw a bifurcation diagram of a similar kind, which you can find in the reading. We're out of time, so I'm not going to go into it. And that bifurcation diagram basically tells you when this fixed point is stable versus unstable, and when you get the onset of these limit cycles, right? And that kind of bifurcation is called a Hopf bifurcation, HOPF. Okay, so we're out of time. So So we will end here. In the next class, we will continue talking about two species models, but we will talk about another kind of Lotka-Voltera model, which is the Lotka-Voltera competition model, where we model species that are competing with each other for various things as opposed to being of the predator-prey type. And we'll also use that class to build up to what might happen when you add more than two species. Yeah? All right. Now you're all free to go. I'll hang out here if any of you have any questions.
So
Yeah.
this one
Yeah.
just states that whatever you have written, whatever you have drawn.
Yeah. Yeah.
There is no perfect statement here, like how it came out.
How it came out, meaning how to find that loop?
No. On what basis this theorem to
Okay, you're asking for the proof.
prove for like how it got constructed.
Okay, so I mean, I'm not going to go into the proof, but I can give you an intuition, right? Yeah, so the intuition is really basically that, let me just draw the basic version, right? You have these two things that you want, right? These two this sort of donut shaped region. Here, all of your trajectories are coming in, right? Here, all of your trajectories are going out, right? And you know that your trajectories don't do funny things like suddenly vanish and so on and so forth. You know all your trajectories don't intersect. Well, now you can see kind of, and so that if they have to stay within here, sure, there might be some loop around which they go around and settle to. Right? And that's the intuition for where it
How
comes
did
from.
we come up with that donut shape? Like, how did that donut shape work? How was that set determined? That donut shape.
Oh, you don't, yeah, this doesn't need to be any specific donut shape. You just, the question is just whether you can find one. If you can find one, then you're done, right? And so we were just doing this thing of constructing one. So, right, so at least one part we knew here from the instability of this fixed point. The other part we constructed by these Kolmogorov conditions.
So what is Kolmogorov conditions?
So the Kolmogorov conditions, and as you see in this reading, is just the statement that you can, that at large x and large y, all of your trajectories come back in rather than go out.
Why don't you use discrete models? Because it could make more sense.
What do you mean by discrete models?
It's all continuous, X can be anything, but the data we have for like the Fox,
Yeah,
it's like discrete numbers.
yeah.
Why do we study discrete models? Because things do change, right? Because if you have a finite, you have countable points to do eventually get cycles if you are traversing through this space.
Yeah, so that's a good question. Why do we work in continuous x's and y's? And sort of one of the ways of thinking about it is that this would be a good approximation when the population sizes were large, right? Because then, of course, you still take continuous numbers, but that thing is small. And so that's sort of one way to think about it. The other is that, look, this is not meant to be a model of any particular system, but it's supposed to be a simplified model which displays the behavior and the phenomena that we are interested in understanding, right? It's one setting, in kind of like when we do physics, we talk about simple pendula and so on and so forth, and we ignore tons of things, right? And the idea is, can we construct a toy model which has the same properties and phenomena that we want to learn about?
Just outline one question.
Okay.
Hello, Professor. Can you hear me?
Yeah. Hi. I can hear you.
Right. When we were discussing the model, we had said that if D increases, we surprisingly see that the predator population does not change, right?
Yes.
But if D were to increase, wouldn't A implicitly also increase, and
Why would
therefore the
A
predator
implicitly also increase?
because if the predators are dying out, then less prey will die, and A implicitly has the death rate of the prey inside it.
I see. Okay. No, that's not true, because when we wrote down the equations for the predator-prey model, we split we split two parts of the contributions of the prey's death. One is its natural death rate that goes into AA, but the other is the death rate that comes due to predation, and that was a separate term, dxy, that we took, right?
Okay.
Yeah, so the natural death of the prey is an A. A is actually some birth rate minus death rate.
Okay, that makes sense. Thank you.
Yeah.
And hunting thing what you were.
Yeah, yeah.
That is like continuous hunting, right? You are hunting continuously.
Yes, yeah. You go every day and you shoot the bears. Yeah.
Only then that will change the effective.
Correct. When you stop it, you'll go back. When you stop the hunting, you'll go back.
Else it will be like just by doing from itself.
Exactly. Yeah.
Yeah, so on what I said earlier, like I was guessing that back then we didn't have computers, so maybe continuous stuff is much more somewhat comfortable to analyze. You can just draw curves, but like now we do have computational power. We can just write discrete equations and just see how things would work out. So is that what we do?
Right. I mean, it depends on, really, like I said, it depends on what you want to do, right? Why do you want to write these equations and study them? If the question is that you really want to go and model in a particular system because you want to predict something about it, then of course, there's much more things to worry about than should you take a continuous or a discrete version of this equation, right? But if you just want to understand what is the minimal model which has predator and prey-like behavior that shows limit cycle oscillations, well then this is fine, right?
Why do we want limit cycle oscillations in predatory models?
Good. Yes, great question. So remember that we had a few observations about predator-prey oscillations. One was that there are oscillations. Second is that there's a phase lag of pi by 2. The third was that there seems to be a well-defined time period and amplitude that seems to be there as you observe them over a long time. So these three features will only be present in these limit cycle type oscillations. They aren't present in neutral orbits, and they obviously aren't present in damped orbits.
There's one more question.
Yeah.
Yeah, hi sir. So in the second model that we studied where there was no predator satiation, so in that case, if K was small enough and we got two stable fixed points, so will they have like different basins of attraction or how would it look like?
Good. So you're talking if my K is small enough that my K comma 0 becomes a stable fixed point. Is that right?
Exactly, yeah.
So there actually you can go into the calculation, you'll find that the other one becomes an unstable fixed point.
Oh, wow.
Yeah, so you don't get two.
Okay. Thanks.
You can't have two stable fixed.
You absolutely can. And in fact, in the next class, we will see cases of two stable fixed. I mean, in the last class, you also saw it, right? You saw bistability. There's nothing mathematically prohibiting it. It's just in these models, you don't see it.
But
Yeah.
if we have two stable fixed points, then there might be an unstable fixed point.
Maybe. Yeah. Or there might be just some separatrix that separates the two basins of attraction. Yeah. As the number of dimensions increases, it becomes hard to say whether or not they have to be another stable or another unstable fixed point. That's why I said maybe.
In 1D.
In 1D, there has to be. Because that's just because you can see that's in 1D you're much more constrained, so you have to have that. Okay, we're all free to go. Yeah. Sure, come. Yeah, and you can also come to me if you want to ask more questions. Yeah.
There's an online participant that are asking to recording the session.
Yeah.
It's available after this class. It's available.
Okay, like I see.
Okay, so they're asking this class.
Yeah.
Can give, right?
Yeah.
Can you tell them to online because online participants?
Okay, but we'll put it on YouTube or something, right?
I think we are keeping in the recording.
Okay. Yeah, I mean, like for the online participants, we will have recordings available of the lectures.
Yes.
Yeah.